In this video, we're going to create a hub and spoke topology with a dynamic virtual tunnel interface on the hub using IKE version 2. Let's jump in. In an earlier video, you and I took a look at using dynamic virtual tunnel interfaces, but that was with IKE version 1. Now we're going to do it with IKE version 2, and here's how we'll do it. We'll create the dynamic virtual template on the hub, and then on the spokes, we can have static tunnel interfaces. And so on the hub with the virtual template, when it gets request, it'll go ahead and clone that virtual template, create the logical virtual access interfaces for its connections out to each of the branch sites. Now in doing that with IKE version 2, we're going to do one additional step that we haven't done previously with IKEv2, and that is we are going to add that virtual template or refer to it inside of our IKEv2 profile. And that's the additional configuration regarding our profile on the hub to make that virtual tunnel interface work. So we're going to begin by creating our certificate map that says if the issuer's name contains CBT nuggets, just like we did in our previous video, then this certificate map will give 2 thumbs up saying yes, it's a match. So this syntax has not changed from the previous video. Next, we're going to play with the defaults. Let's first of all reset the default on this router for the IKEv2 proposal back to the way it was from the factory with the command default crypto IKEv2 proposal. Now please be aware that if you're in a production environment and someone else is using a customized proposal and then we issue this on a router, this changes any customization they may have done to the default proposal back to the defaults. So please be careful in a production environment before changing anything back to its defaults so we don't break any other part of our configuration. So now that we know our default is at a clean starting point, let's go ahead and customize our default proposal. We'll do that by setting the encryption to AES CBC 256, the data integrity, the hashing for SHA-256, and let's use Diffie-Hellman group 14. So we've just modified the default IKEv2 proposal and its 3 key elements, the encryption, the data integrity, and the Diffie-Hellman. It's also really important to verify that the changes that we put in place are actually what's happening. So let's do a show crypto IKEv2 proposal default just to verify that the commands we put in to customize this default IKEv2 proposal, just to verify that they took hold. And it appears that they did. So AES 256, there's our SHA-256, the Diffie-Hellman group 14, and the pseudo-random function that IKEv2 uses is simply going to follow the hashing method that we specified. Next, because we are in a test lab environment, let's also go ahead and set back to its defaults the crypto IKEv2 policy. And then we'll do a show command, show crypto IKEv2 policy default, just to verify that it has the default parameters. And primarily we want to verify that this IKEv2 default policy is pointing to the IKEv2 default proposal, which it is. Next, we're going to create an IKEv2 profile. Now in the profile, we're going to specify the authentication method and our matching criteria. So most of the syntax is going to be identical for this profile as what we did in the previous video with the site-to-site RSA signatures for authentication. However, there is one additional tag, one additional line that we're going to add to this IKEv2 profile if we are using a dynamic interface, a virtual access interface on this router. And if we are using the virtual template to create the virtual access interface, we need to specify that right here in the IKEv2 profile with the syntax virtual-template and then our template number that we are going to create here in just a moment. So this way, when R1 and R2 are initiating and building the IKEv2 tunnel based on our certificate map, which means that we're looking for in the certificate that we're receiving from the peer an issuer name which has in it CBT nuggets, and if that's the case, how are we going to authenticate? We're going to use RSA signatures. What's our trust point going to be associated with the digital certificates? And which virtual template do you want to use to go ahead and create or clone out the virtual access interface? So to be clear, the added reference to the virtual template is the only difference so far compared to our previous video where we did a static site-to-site tunnel. Next, let's move into the parameters for the children essays, the IPsec essays. We have a default transform set. I'm going to go ahead and default it back to its starting position with the command default crypto IPsec transform set. And remember, in a production environment, we'd want to be very careful about who was previously using that default transform set, because if someone had customized it and was using it, and now we're setting it back to the default, that's going to cause something else to possibly break. So now that it's defaulted, I want to do some customization of our own. And to do that, we're going to type in crypto IPsec transform-set default, and let's use ESP-GCM256. Now, GCM, which is part of that next generation encryption, GCM includes not only the ability for encryption services, but also data integrity and authentication services. So if we're using that, we don't need to add on top of that SHA HMAC or MD5 HMAC, because the GCM has the data integrity portion as well as the confidentiality built into it. Now, to be clear what we're working with, let's do a show command of show crypto IPsec transform set default, just to verify that what we put inside that new customized default transform set is still there. And this looks great. It's using transport mode, and that was from the default transform set before we modified it. And it's also using ESP-GCM256, because that's what we told it to do right here. That looks great. Now I'd like to ask you a question. Who, by default, uses the default transform set? And you're saying, Keith, I know. It's the default IPsec profile that calls upon the default transform set by default. And you'd be absolutely right. So also, I'm going to default the crypto IPsec profile. So if any other customizations have been done to it, I'm going to reset it. And let's do a quick show crypto IPsec profile just to confirm what those defaults are. So in our IPsec profile, it's calling upon the transform set default, which is this guy right here. So in the brackets, it's just describing the transforms that we have as part of that transform set. PFS is off by default, and it has a default lifetime of this many kilobytes and 3600 seconds. And those parameters are specifically for the children essays, the IPsec essays. Now, what we need to do for this default IPsec profile is we're going to modify the default IPsec profile, and inside of that IPsec default profile, we're going to refer to the IKEv2 profile. That's the profile that specifies how we're going to authenticate with the peer. That's the profile that indicates how we're going to match identity. That's the profile identifying our trusted CA. That's also the profile that's identifying the virtual template that we're going to use to create a virtual access interface. Next, let's create the virtual template. We need to call it virtual template 1 type tunnel. The reason we need to call it virtual template 1 is because in the IKEv2 profile, we pointed to virtual template number 1. So we could have used a different number, but if we did, we'd have to use that in both places, in the profile as well as the template itself. And since we've been through the configuration of a template as well as tunnel interfaces multiple times, we'll do this a little bit faster. We'll play the IP unnumbered game. We'll specify the tunnel source, which is Ethernet 00. We'll specify the tunnel mode of IPsec IPv4. We'll place the IPsec profile on this template interface with the command tunnel protection IPsec profile default. And then we'll also put this virtual template into OSPF. So that any virtual access interfaces that come up as a result, they'll also be part of OSPF. Now the configuration over on R2, we're going to use a static tunnel on that side. So all of the ingredients that we're going to put here on R2, we've already seen previously in the previous video on site-to-site using RSA signatures for authentication. And we need to make sure we have compatible transform sets and policies and profiles that can match up and be agreeable with R1. So on R2, we'll go ahead and create our PKI certificate map. We'll call it CMAP. We'll use sequence number 1 here. Again, if you have multiple entries in a certificate map, they're processed in order, looking for a match. We're going to match on the issuer name containing CBT nuggets. Because this is a lab environment, I am going to default whatever's in the current crypto IKEv2 proposal, and then we'll customize that default IKEv2 proposal using the encryption, data integrity, and Diffie-Hellman group that are identical to the IKEv2 proposal that we customized over on R1. It's probably a good idea to verify what's there, so we'll do a show crypto IKEv2 proposal default. We could also leave off the keyword default and it would show us all the IKEv2 proposals. And that looks great. It matches up with what we put in. Now next, because I am in a test environment, I'm going to go ahead and default the crypto IKEv2 default policy as well. And then let's just show it to make sure we know what's in it. We'll do a show crypto IKEv2 policy. And we have 3 basic ingredients. We have the matching for the VRF, the matching based on address. Those are wide open by default. And the most important part of this is that it's calling upon the default IKEv2 proposal, which is perfect because we just customized the default IKEv2 proposal. Next, let's create our IKEv2 profile. We'll name it IKEv2-profile. We'll specify that for identity. We're going to use our distinguished name, which is pulled from the certificate. We're going to do a match based on our certificate map called CMAP, which is looking for CBT nuggets as part of the issuer name from the CA who issued those certificates. For authentication, we're going to do RSA signatures for the remote side as well as the local side. And we also need to specify the PKI trust point that we're going to use for the authentication of the digital certs. Now here on R2, because we're not using a dynamic virtual tunnel interface, we don't need to include the virtual tunnel interface information inside of the IKEv2 profile. On R1 in the IKEv2 profile, we included the virtual template interface it should use to create a virtual access interface for that IPsec connection. Now let's move on to IPsec, the child SAs. Let's default the default crypto IPsec transform set. So whatever currently was set, we're going to wipe that out back to its default, and then we're going to customize that default transform set with crypto IPsec transform-set default, and let's use ESP GCM 256. Why? Because that's going to match perfectly the transform for the IPsec tunnel that R1 is expecting to negotiate and build. And it's always a good idea just to do some show commands and verify what we've configured. Let's do a show crypto IPsec transform-set default just to verify that what we put in is what's currently there. Now what is it exactly that uses the default transform set? Well, by default it's the default IPsec profile. And if we want to default the IPsec profile to make sure it's back to its starting point, we can do a default crypto IPsec profile, and then we'll do a quick show crypto IPsec profile just to remember what those defaults are in that profile. So in the IPsec profile, it's calling upon the transform set called default. It's got a default lifetime for that IPsec tunnel and is not using PFS by default. So we are going to make a teeny little customization to the default IPsec profile, and that is we're going to go into configuration mode for it, crypto IPsec profile default, and we need to tell it which IKEv2 profile we want to have associated with it. And we do that with the command set IKEv2-profile and the name of our IKEv2 profile. Next, we're going to go into interface configuration mode for our tunnel interface that we're creating. We're going to specify IP unnumbered loopback 0. We're going to specify the source of this tunnel, which is E00 here on R2. We're going to specify the tunnel mode, which is IPsec IPv4, and the tunnel destination, which is 15001. That's the reachable IP address over at R1. And to apply this, we're going to do a tunnel protection IPsec profile and the keyword default, representing we're applying the default IPsec profile. And let's also tuck this into OSPF process 1 area 0. I just love it when a tunnel comes up and it seems to be working. And the fact that it did come up, the tunnel interface just came up, and our OSPF neighborship also came up. Those are two very, very positive signs that we've got some good connectivity. So let's do some basic verification. Let's do a show crypto IKEv2 SA to take a look at the IKE version 2 Security Association. That looks great. So the lifetime is the default of 1 day, and it's currently been up for 68 seconds. And it has the parameters that it's using for that IKEv2 tunnel, the encryption, the hashing, the Diffie-Hellman group, and the authentication. If we want a bird's eye view of how things are going, we can use the command show crypto engine connections active, and that'll show us the IKEv2 tunnels. And if we have some IKE version 1 tunnels, they'll also show up. And if we wanted to look at the further details of those tunnels, we could do a show crypto IKEv2 SA detail or show crypto IPsec SA to see more details and more information about those tunnels. We should have some routes in place. If we do a show IP route OSPF, R2 says, yep, I've learned the 10.1.1 subnet from my good buddy R1. It's reachable through my tunnel interface. If we do that same command, that same show IP route OSPF over on R1, it should show that the 10.2.2 subnet is reachable via its virtual access interface. And sure enough, there's the 10.2.2 network, and it's reachable via virtual access 1. That was cloned from the virtual template, a logical interface that R1 is going to maintain for its IPsec tunnel between it and R2. And if we wanted to ping, we should be able to ping from either side. If we do a ping to 10.1.1.1 and source it from 10.2.2.2 over here from R2, that should successfully be sent over the tunnel. R3 and R4 are two additional branch offices. If we applied that same configuration that we did to R2, R3 and R4 would also have that connectivity up to the hub. And in that case, we'd now have a hub and spoke, with the R1 being the hub, R2, 3, and 4 being the spokes. So to verify on R3, we could do the command show crypto IKEv2 SA, or we could add on the keyword detail to see more information on that security association. And this is indicating it's between 35003, which is R3's address, and 15001, which is R1. To see the IKE version 2 and the children IPsec tunnels, we could use the command show crypto, engine, connections, active. And now with 3 spokes, R2, R3, and R4, all having built their connection up to the hub, if we do a show IP route OSPF, we should have additional routes we've learned through our tunnel interface. And you'll notice from R3's perspective that each of these networks, 10.11, 10.22, 10.44, are all reachable via the next hop of 1.1.1.1, which is the virtual access interface on the hub R1. To test connectivity, we can do a simple ping. We'll ping to 10.1.1.1. We'll source it from 10.3.3.3, and that works. And we'll ping 10.2.2.2, that's the subnetwork behind R2, and we'll source it from our local 10.3.3.3 on R3. And also we'll ping 10.4.4.4 from our same source address of 10.3.3.3 just to verify we have full connectivity to there and back. Now to verify the path between R3 and the subnet of 10.4.4.4, we could issue a trace route. So we'll do a trace route to 10.4.4.4, source it from 10.3.3.3, and this indicates that we are routing through the hub. So now we have a Flex VPN hub and spoke topology with a dynamic tunnel interface at the hub with static tunnel interfaces at the spokes. I have had a great time in this video. I'm so glad you joined me for it. I would strongly encourage you to practice everything that we've done in this video. And to assist you with that, I'd like to share a couple documents with you. Number one is the Hub and Spoke Dynamic VTI Flex VPN with IKE version 2 document that's in the Nugget Lab files for this course. And it has all the configuration and verification commands that we used in this demonstration to implement the dynamic VTI on the hub and the static tunnel interfaces on the spokes. I've also placed in the Nugget Lab files for you this document called Final Configs Flex VPN Hub Spoke RSA Signatures that has the full working config for R1, R2, R3, and R4, which was their final resting state after we did all the configuration in this video. So again, thanks for joining me. I hope this has been informative for you, and I'd like to thank you for viewing.